So, welcome everyone. Before Christian takes it up to give the second lecture in the CFT basics, thanks a lot for all putting your names that I can recognize who to accept from the waiting room. And a second comment is that there will be a new link every day, well, for every pre-course. So be sure to click on the right one, and you can take it from here, Christian.
All right, thank you so much. Let's see, before I start, I actually want to, hold on. One comment that I forgot to mention, like in the overleaf, in the notes that you can see, all of the section titles that are written are, for instance, 2.3.2, say, and I only wrote yesterday 3.2. So just for your orientation, that you know that these are actually still the same. Just put a 2 in front. All right, and then the other thing is I noticed a minor mistake that I had in the notes and also here in my preparation yesterday in the lecture. Section 3.2. Hold on, where is it? Section 3.2. Here we go. That I called that local conformal transformation, but that's actually not the correct section title. The correct section title should be the conformal group in 2 dimensions. I hope that doesn't cause too much trouble. All right, so I will first do a recap of what we did yesterday, and then I will give you some time to ask questions if you have some. So let's start with a small recap. So we talked about what a conformal transformation is. Those are basically given by this equation where you just have a rescaling of the metric upon applying a transformation f. And what these things typically do is that they just reshape a manifold in a way that preserves angles, but not necessarily lengths. And then there was this exercise that I'm not sure how many people tended to. Oh, by the way, I plan to provide solutions to all the exercises that I will have presented yesterday and today. I will try to upload the solutions before the next meeting. So that's probably Sunday. But before that, I'd hope that you guys take a look and see if you can solve these problems. Okay, so then we had conformal transformation in general. There is an example that I asked you to evaluate, and more importantly, there are 4 types of conformal transformations, which we call generators. And here I forgot that here's one comment that lambda is just so capital lambda is just lowercase lambda squared. That's here, in case that that you wondered why there was like the blank field. And okay, we have translations, rotations. If you have learned quantum field theory, you're well aware of these two. Those are just they compose the Poincaré group. And then additionally, and this is what comes in CFT, you have the dilations and special conformal transformation. Right, so we talked about those. I just said I didn't really derive or show to you that the conformal group is SOP plus 1 comma Q plus 1. And then I started talking about 2 dimensions. And the first thing we did is we discussed the 2-dimensional case of the transformations just discussed. Then what else did we do? We introduced the Möbius group and argued that the Möbius group encapsulates all these transformations of before, like the ones in this table. So that's the Möbius group given by this relation here. And what else did we do? Okay, right. And then we started talking about the actual, like this is the, I guess, the most crucial part of yesterday, or the most non-trivial thing of yesterday that we started to discuss, is that there's this claim that conformal transformations in 2 dimensions are actually holomorphic and anti-holomorphic functions. And I showed you one direction in the sense that I showed you how holomorphic functions are conformal transformations. So they do rescale the metric. And there's an exercise where you show the other direction. Let me know if you have questions for that. And I went on to discuss a few remarks, of which, well, let's see. Well, I guess the one which is noteworthy here is that we're actually going to be talking about Laurent series. That means what you're going to see in this course is a bunch of gymnastics with singularities, and you'll see that it's actually quite neat, super nice. Okay, so other than that, now you have a few minutes or like a chance to ask questions if you have some so far for what we've discussed yesterday.
Just a curiosity question. What will happen if one decides to attempt, instead of using 2 spatial dimensions, to use 1 spatial dimension and 1 temporal dimension for defining all this algebra?
The algebra is still going to be the same. So you can actually show that this structure here. What do you mean with this algebra? Do you mean the claim here that we
sorry,
made?
yes, with the claim, yes. Sorry, I missed sometimes the correct vocabulary.
They're going to be, hold on. So the structure persists. So that's the bottom line. I'm not quite fully aware now what the functions are called. They're not really holomorphic, anti-holomorphic, because you're not working on the complex plane. But you still have the infinite dimensional symmetry if you're working with Lorentzian signature instead of Euclidean signature. I will let me make a note and look up for you what the actual terminology of how the claim is modified, and I will hand that. I will tell you next time, or I will send an email. One sec. What is 2D?
Oh, thank you. I guess later on in the course, I will like to go back to this, because normally Chern-Simons is defining 2D, one thing immediately to the spatial dimensions.
Yeah.
But yeah,
Right,
that
so
is related to that. Yeah.
Yeah, most of the structure is easily seen that you just have to wig rotate. So will I actually do that? I may upload an exercise sheet for the free boson. I'm not sure yet. It depends a bit on how far we progress. But in essence, it's really just a wig rotation. So that means time. Let me just make that here. So time, physical time in 1 + 1 dimension is just relegated to Euclidean time, tau. Don't nail me on the ± sign here. I'm not quite certain, but you know, I guess you're aware of this construction. But so yeah, in principle, it holds all true. It's true that for Chern-Simons, what you have typically, say, you have a Chern-Simons theory in a cylinder, in a solid cylinder. Then on the boundary, the mantle of the cylinder is going to be, there's going to be a CFT, a chiral CFT. It's true. All right. Other questions?
Excuse me?
Mm-hmm.
Yeah, so yesterday we said that the global conformal group is like the Mobius group, which is finite in 2D,
Yes.
in 2 dimensions.
Yes. Mm-hmm.
But then we said that we can extend it to be infinite dimensional, because it is in a one-to-one correspondence with the holomorphic, anti-holomorphic functions.
Good,
So
very good.
it's not really clear to me.
No, it shouldn't be yet clear. Good point. It's good that you have this question, because it's true, like this thing here is finite dimensional, and not every holomorphic and anti-holomorphic, well, in this case, holomorphic function is going to be of this type here. clearly, not every function. So the Möbius group is just going to be a subset of the conformal transformations, and we're going to progress on that, well, nowish actually. So that's the next point on the menu, I think. Let me just see that I don't lie. Yeah, we're going to see now how these things differ.
Thank you.
Or how this is extended.
Thank you.
Hello, I had a sort of simple question.
Mhm.
How do I think of conformal symmetry or scale invariance when like the base space is a closed manifold? Like say I have a sphere or a torus. So what is the analog of that? Like I understand like on the real plane or like on the complex, like on the Riemann sphere, but how does that work on the, like
So
say
you
I have,
want, say, hold on. You said you understand. You want a closed
Yeah.
manifold. I
yeah,
don't know, a donut, torus, say,
yeah, sphere or torus or
or
something.
sphere.
Yeah.
Keep in mind that these transformations are all going to be local.
Okay.
So what they do, so they're going to have local and global properties, but typically it's actually the way you think about it is that you only select a local point and you look at the transformation in that surrounding. That's how it's set up. Other than that, I mean, you can sort of basically, oh, I'm very bad at drawing, but you should be able to deform the torus in one way or another, or the sphere. Would that be? Oh, I dare not draw something. Well, yeah, I dare not draw something, but in principle, I like to think of conformal transformations as local things. So I pick up a patch, like I said, and I transform it here. And sometimes I need to watch out for global transformations. Sorry, for global properties.
So at least for local transformations, then the dimension is as long as like the space is locally Euclidean, it's going to be the same. Like the dimension
is always going to be the same in our case. Like we're looking at transformations which don't mess with the dimensions. We're looking. We said that in the beginning. Maybe I didn't stress it. What we're going to do, so we have these manifolds which at this stage can have different dimensionalities, but then we very quickly restrict it to the case that they are actually the very same manifold in disguise.
Okay, thanks.
Okay, so let's get started. Thanks for the questions. So the next thing that we want to talk about is point 3.3, which in the overleaf, like I said, is 2.3.3. But I'm not going to write 2 always ahead of the section number. Okay, and that's classical conformal generators and the Witt algebra. So, okay, so what we're going to do now, something that is very typical, is in at least when considering Lie groups, is we're going to consider infinitesimal transformations, holomorphic, and or meromorphic, actually, like I said, meromorphic transformations. And those have a Laurent expansion. And the Laurent expansion, just let me remind you. So suppose I have a function wz. This is my conformal transformation. And if this is supposed to be infinitesimal, it takes the coordinate z and it just shifts it infinitesimally by some small parameter epsilon. And what I mean by this having a Laurent expansion is that I can expand this into a power series with including negative powers. So let me be very clear. So n is in z, and then I have n plus 1. And this 1 here is just convention. And you'll see in a moment why it's convenient. And I want the complex parameter epsilon n to be small. That's what I do. And in principle, if we wanted to, and it's not going to be important really, but I'm going to say that there is a transformation GW, which implements the change of Z to W of Z. It's not going to be super duper crucial though for what we're going to do. Okay, so this looks very abstract now. Let's get a feeling for this. So let's go ahead to obtain a feeling. For this, we're going to pick a single n. I'm going to pick a single n. That means now I'm going to take a function. I'm going to give it a small label, subscript n, which is just z plus epsilon n, z n plus 1. So instead of the sum, I now just take a single one. And as before, epsilon is a small number. And I can associate, I'm just going to declare that there is a generator, Ln, a generator in the sense that it's not a group element, but it's in the exponential, it's like a group element is the exponentiated generator. So this is the generator, which does the same thing. So it generates a transformation, Wn of z, that's what it does. And now I'm going to take a few examples, and I hope that you'll recognize them. So in particular, the global, what we declared yesterday to be global, and I'm going to be a bit more concrete in a moment for where this terminology comes from. Global conformal transformations correspond to, so let's look at n equals 0 and plus minus 1. For instance, translations, I called them T yesterday. Those are generated by L minus 1. Why? Well, we just go up here and we check what happens for L minus 1. Well, the function z is mapped into z plus epsilon, where epsilon is a small complex parameter. So that's just a translation, right? So there's no magic going on. Then there were the rotations, dilations, which I called R and D. And those are going to be generated by L0. Why? Well, we do the same thing. We know that rotations and dilations, like the complex version of that, just takes z into lambda times z. But if lambda is just a small dilation, then what this really is, it's 1 plus epsilon z. And then we go and we look up here again, and we find that this is indeed L0, right? So in that sense, L0 is responsible for those. And then we had the special conformal transformation. I'm just going to write SC. And this one is L plus 1. And here we have to think a bit harder, but it's not too complicated. I'm just going to give you the solution. Hold on. So the solution is, so this was the special conformal transformation, epsilon z plus 1. And then you expand for small epsilon and you get something like, z plus, yeah, z plus epsilon z squared. That's what you get if you do this right. So this is really just a Taylor expansion. And then you go again and you see that this is, if you pick n being 1, then you get z squared. So that's what you want. So in this way, what we're doing now is we're taking the global conformal transformations that we got acquainted with yesterday, and we're putting them in the framework of these complex infinitesimal generators of conformal transformations. Okay, so that's good. That's good. So I remind you, translations are so the generator of translations is momentum. The generator of rotations is typically angular momentum, and the other ones we're going to discuss them. Well, special conformal we won't discuss much, but the generator of dilations is actually important, and we're going to discuss that one in a bit more detail, but not yet. Okay, so all other. So in a moment, we'll see that all other n, so meaning n, all other n, let's make this like this, which are not in that set, are called local transformations, well, conformal transformations. I'm just mentioning this here, and I'm going to argue in one moment why this is the case. Let's give this another color. Actually, let's not give it yet another color. I'm going to do it in a moment. So in the notes, so I derive derivation of the action of ln on a function. So, and what you find is, so I'm not going to do that here because it's rather mathematical details with little physics inside, and time is short. But I invite you to go read the notes. Like as you'll see, I'm forced, like, because we don't have too much time, and this is not like a hardcore CFT school. I will place more emphasis on telling you physical properties than on mathematical derivations. But all the mathematical derivations I've went through a great deal to write them up in the notes for you. Okay, so ln acting on a function is going to look as follows, like this, or so this is a function of z, or that means that ln can be just written as n plus 1 del. The mathematician says that it's represented on functions as follows, and they typically write pi of ln is this here, but we won't be as pedantic here. Okay, so let's take a look at this. So now we're actually in a position to be more concrete about global and local stuff. So for whoever had the question before, now's the time to pay attention. So you take a look at this thing, right? It should be clear here. Let's move this here a bit. Now let's keep it here. And let's write n is an integer number. In particular, it can be negative. Okay, so what we see is that this thing here is well behaved at z equals 0 only for, let me just see, well, you can read it off. If the power is negative, then you pick up a singularity. So, so we need n to be bigger than -1. Or equal. So this is bigger or equal. So the other problematic point is infinity. So we want to study z equals infinity, and what we're going to do is we're going to take z equals -1 over w, and we're going to study that for w equals 0, and then I'm just going to tell you how the partial derivative transforms. it transforms as such, then you can just plug everything in, and what you find is that the generator now looks as follows: n-1 del W. Okay, so now you look at this and you see that this is well behaved at W equals 0 only for, actually, let's take a different color. I'm going to change this here, n bigger or equal to -1, and here it's n smaller or equal to +1. Oh, I made a mistake, did I? No, I think that's okay. All right. So what you see now is that the intersection, so the things, so how do I draw this? I'm just going to write it. So for n equals 0 and ±1, those are always well behaved. They're well behaved for at z equals 0, and they're well behaved at z equals infinity. And the generator doesn't have any other point where it's problematic. Remember that we're working on the Riemann sphere, so that's why infinity is allowed. So well behaved on the Riemann sphere, always, so to speak. And all others, ill-behaved somewhere on the Riemann sphere. And somewhere meaning either 0 or infinity, that's where the generators become problematic. And that's why we call them local. Okay, so back to the, maybe let me stress the question that was before. So you see that these here about the locality and the extension of the conformal group. So these things here are basically the generators of the Möbius group, right? So here we include the Möbius group, and we have seen that those are only L0 or L ±1, but we have an infinity of generators, and all the others are these local generators. They're still symmetries, it's just that you have to be careful where you want to study them. Like, for instance, like I said, this first class here, at z equals 0, you can study every generator with n larger or equal to -1, for instance. All right. Okay, so there's an exercise now. So the first thing that physicists like to ask when I give them, or when given generators, is you want to know how they talk to each other. So, and what you're going to do in an exercise, this is a simple one. Do that for your self-esteem. So show that the Ln furnish the, and this is an important one, so let's put it in red, the Witt algebra. So in the Witt algebra, oops, blue. Witt algebra is Ln, Lm equals to n minus m, Ln plus m. And n and m are integers. N comma m are integers. This is just a commutation relation like you would have for a free boson, for a free fermion, for SU2, and it's just a different commutator. And the one marking difference is that the number of generators is now infinite. Like for SU2, you have 3 generators, right? You have usually when we write it in terms of ladder operators, we have J plus, J minus, and J3, and so on. I think you know what I'm talking about. Okay, so this algebra, the Witt algebra, is the algebra of classical, let's make this in a different color, classical conformal transformations. Okay. So far, so good. Now, if you've counted, obviously, you may remember that yesterday I insisted that we have 6 generators for the conformal group. And now I still owe you, so I only discussed 3, and I still owe you another 3. And the anti-holomorphic sector equally has its Witt algebra. So it's treated analogously. And then you have, we give them a bar, but it's an ln just like the other one. And surprise, surprise, you just replace z by z bar and del by del bar. And you also have an infinity of these. And now I can be a bit more precise. Oops, maybe I shouldn't. If I at some point like slide away something that you're copying, just let me know so I slide back. Right, so the global part, so let's collect. We have two translations which are generated by L-1 and L-1 bar, right? We have 2 special conformal transformations, which are L1 and L1 bar. And we have 1 dilation. And the dilation is actually going to be L0 plus L0 bar and 1 rotation. And the reason for that is, remember that L0 generates a complex dilation, and we now disentangle them again. So a rotation is generated by L0 minus L0 bar, and then there's just an I out front. Well, if you take the I is just for an exercise I'm going to propose in a minute so that you don't get confused. So first of all, so the number of this is 6. That's good. And now there's an exercise for you. You may be puzzled about me writing the dilation and the rotation in this manner. And so that you get an idea of what that means, there's an exercise. And the exercise is go to polar coordinates. Polar coordinates. Those are just z equals r e to the I sigma. And show that L0 plus minus L0 bar correspond to dilations and rotations. And let me give you a hint here. This hint is not in the notes. So that means that the dilations are generated by del r. So this is dilations. And rotations are going to be generated by del sigma. And it's up to you to relate these two. Right? So you have an expression in terms of partial derivatives of L0. So this is partial here you have it. For instance, L0 bar is a partial bar. Somewhere above I've given, well, actually all that you need is this relation to write how the partial derivatives of R and sigma relate to those of Z and Z bar. So this is just an exercise essentially in differential geometry when transforming tensors, but it really just confirms to you guys that that dilations and rotations are indeed given by these generators. Okay. So are there any questions for this part? Okay. So the next point on the menu is quantum conformal symmetry. So we discussed classical conformal symmetry. And now let's discuss quantum conformal symmetry a bit. Actually, unfortunately, I won't have the time to derive it for you, but in the notes, I spent an entire section deriving for you, in particular, the Virasoro algebra. Well, actually, it's not I derive for you, but the reader and the writer derive together, in the sense that I give you exercises, but in principle, I guide you through them. Like the exercises are supposed to guide you through the through CFT, basically. Okay. So upon quantization, the Witt algebra is deformed to and this is perhaps I'm not sure how much CFT literature you read, but Virasoro algebra, oopsie, Virasoro algebra is basically the buzzword associated with two-dimensional conformal symmetry. And the Virasoro algebra looks as follows. So I'm going to write the generators with capital L. And I'm going to write them. So you see there's going to be a term which looks exactly like the Witt algebra. So these are this first term just returns you the Witt algebra. And then there's going to be a deformation. And this is called a central extension. And I'm going to say a few words on that in a minute. And N, M, R, and Z. Okay. So.
Excuse me.
Yes.
In which sense was the discussion before classical, and are we now going to the quantum regime?
Yeah, that's a good question. Unfortunately, so I have not, like, up until now, I'm just declaring. Before it was classical because we never talked about Hilbert spaces, right? All I talked about was a space of functions, a manifold, so to speak. Like in classical mechanics, you talk about particles rolling down a hill, for instance. That's just a particle on a manifold, right? And transformations on this system. So in that sense, it's classical. When we want to talk about quantum theory, we have to, strictly speaking, start okay, there are many ways of doing it. In free field theory, we start from a classical action and we promote the fields to be operators on some Hilbert space. I haven't done, that's the idea here too. So the LNs and LMs, the capital LN, capital LM, they are going to be operations on a Hilbert space. And for now, I'm just declaring that this is the quantum version. I'm not deriving for you that like how you arrive at this result. I am going to provide two examples. I hope I'll get to that toward the end of the session, where you have the free fermion and the free boson. And with the free fermion and free boson, what we're going to see is that this term here, this deformation, is going to be a quantum effect. Quantum effect. I'm going to talk much more about Hilbert spaces in the CFT in a moment, but I'm afraid that for time reasons, I'm just going to have to ask you to bear with me and just believe me for now, that when you go quantum, the Witt algebra is indeed deformed as claimed here. I hope that's okay. I hope you can bear with me. Thanks for the question. Let me say a few words. So I'm going to say a few words, and maybe then in the moment also something for whoever works on topological insulators. There's the word anomaly falling in a minute. So first of all, so the deformation is called central extension. Central extension. And central extension, because we say that C is an operator, C is a central operator. And central in the mathematical literature, I'm not sure how often one encounters it in the physics literature, but central means that it commutes with everything else. And clearly it commutes with itself. So in principle, it's going to act like the identity. So there is a powerful mathematical theorem, not theorem, it's a lemma. It's called Schur's lemma. Schur's lemma. And Schur's lemma allows us, so we're going to work on irreducible representations. So on irreducibles, so these are unfortunately now just a bunch of words, but for now, all that I want to conclude, so if these words don't make any sense to you, don't bother, don't be scared away. The only conclusion of this is that we can basically think of this C hat as a number C. For our purposes, it's going to be a real number, and it's going to be just multiplied by the identity operator. That's it. So the whole point of my little excursion here was to say that we can really just think of it as a number, full stop. Nothing scary going on. And we're going to write always, so in the future, right, so I'm only going to write only this. So this is what I'm going to do in the future. I'm not going to write C hat. And the next thing, so if you take a look, hold on. Right, so if you take a look at the deformation, you see that when n is 0, the deformation vanishes, right? And when n is plus or minus 1, the deformation vanishes as well. And that just means that in principle, that's the second remark. So the central term, central extension, vanishes on n equals 0 or plus minus 1. And that means that L0 is, what do I do? Is still dilations, complex dilations. And L1 is still special conformal transformation, or responsible for, like generating that. And L minus 1 are translations. So the physical interpretation, even though I have, strictly speaking, a different algebra now, on these three transformations, the algebra looks exactly the same as the Witt algebra, which allows me to think of these three transformations as in the case of the Witt algebra. But that's sort of a nice aside. And now let me make a comment. So for those of you working on with topological insulators / Chern-Simons theory, I'm going to say a few words now. I'm not going to write that. You can find those words in the notes. So C is an anomaly, but C is not an anomaly. So the anomalies that you encounter in Chern-Simons theory, or say the quantum Hall device, where you talk about the bulk boundary correspondence, those anomalies are typically associated with some topological effect, for instance, the Hall conductivity, which is topologically quantized. This anomaly here is not of that type. It's not a topological anomaly, but it's still an anomaly. Maybe you've heard the term that anomalies are, you take a system which has a symmetry, which is classical, and then you quantize that system, and the symmetry is broken, and then we speak of an anomaly. So the process of quantization messes with the classical symmetry. And here it's similar, and the central charge essentially, when, for instance, CFT is scale invariant. So you would like to have absence of scales, but sometimes it turns out that you can study CFT in presence of temperature, which is a scale, or in presence of a finite extent system, which also gives you a scale. And in that case, the CFT will respond by taking out the central charge. So those are just a bunch of words which are summarized in the notes, but they're not super duper important for what's going to follow. Okay, just as before, let's keep it here. Just as before, so we had a holomorphic copy of, so there's an anti-holomorphic copy, sorry, of the Virasoro algebra. And this is really just given by generators Ln and Lm. It has the same form as above, evidently. And what is now special is that the holomorphic and anti-holomorphic sectors, they commute. Actually, hold on, I forgot to make a comment here. Right here, I forgot to say that for the Witt algebra, likewise, holomorphic and anti-holomorphic sectors commute. Sorry about that, I forgot that. And here you have additionally, in the case of the Virasoro algebra, you have additionally, so you have a central extension C for the left moving, for the holomorphic sector, and you have a central extension C bar for the right moving sector, and in general, sorry, for the anti-holomorphic sector. And in general, they're going to be distinct. For our purposes, we really don't have to think much about them. But for instance, if you think about, again, topological insulators, you're going to have chiral CFTs on the edge of your device. And they're typically chiral typically means that C, say, is non-vanishing, while the other one, C bar is vanishing, something like that. That's what we say, what we mean when we say chiral CFT. Sometimes more generally, we just mean that the central charges do not coincide, and we say this is a chiral CFT. And then what one really looks at is at the difference of the two. But those are just words. Okay. Like I said, I just basically assaulted you now with the quantization. I just told you how the symmetry algebra of conformal transformations, classical one, how it is deformed when you go quantum. And later on, we're going to look at an example where we can actually sort of see that this is the case. Sort of that I haven't been lying to you. So we're going to take the quantum version of a free boson and the quantum version of a free fermion as field theories. And you're going to see that this term, that this central charge term indeed arises. Okay. Any questions? I'm afraid that at this point you may have many questions because so what I said,
Yes.
I didn't derive.
If I may, this Kronecker delta n plus m have just if I satisfy 0. You didn't mention like what is the intuition behind this Kronecker delta, where does it come about, and obviously also if this Kronecker delta is different from 0, this term also vanishes, right?
You want to know if there is a physical way of arguing that it has to be present?
Yeah, like, I don't know. Yeah. I don't know why does this Kronecker delta arise, or is it just the algebra which like the computations?
It's the I have no physical. Let's see. Is there a physical way of seeing that? So, for instance, what this Kronecker delta means is that so say you take L2 and L minus 2, then the central term appears. Like the commutator. If you take the commutator, L2, L minus 2, then the central term appears. Of course, when you take L2 and L minus 3, the central term does not appear, and it just looks like the Witt algebra. I have no physical intuition on why. I can think about that. I'll think about that.
Maybe
Mm-hmm.
related question.
Okay.
Do the L and M, sorry, the Ln, do they have a realization as maybe difference operators on some function space?
Differential operators.
Yeah, or maybe like finite difference operators.
Finite difference operators in the sense of no, what do you mean? I'm afraid, like, I know the term finite difference operator in type binding setups, but that's not function. Is that what you mean?
Or like a discrete derivative in a way.
Well, no, in this case, no, we're not. The Virasoro algebra is a field theory thing. It does not arise on a lattice in a sense. So you can most likely. Well, that's not true. Excuse me. Let me be more precise. If in physical applications, what you typically do is say, I give you a chain, spin chain, and the spin chain has a scale, which is the lattice constant, right? And when you go to low energies, then you basically don't see that scale anymore. And in that case, conformal symmetry can emerge. So most likely what that means in terms of these finite difference operators is that you really take the limit where your finite difference operators become differential operators. And actually they're going to look, maybe I will write it down in a moment. So let's see, here we go. You see that here you have these differential operators. Let's make this with the color, right? So this is a differential operator, and that's what the Virasoro operators are going to look like too. They're going to have a bit more information, but they're going to look like that essentially.
Okay, thank you.
Okay, thank you. So the next thing is so in CFT, there is one protagonist, and it's a protagonist that we have in many places, and it's the energy momentum tensor. Energy momentum tensor. So I won't, because it's not like strictly speaking CFT, I won't derive like, well, it is CFT, but so let me just give you some folklore on the energy momentum tensor. I won't be very precise here, but so what you can do is you can think of the energy momentum tensor as the variation of an action with respect to a metric, where what you do, and this is what we, so there are other ways. For instance, you can take the Northe current prescription and define the energy momentum tensor as the current for translations. I'm not going to do that here because the transformations that we're looking at are intimately related to scaling the metric. So the definition given, this is typically given in the general relativity literature, of the energy momentum tensor being a variation with respect to the metric is more natural. And this is the variation. This is a small thing, a small variation. And conformal transformations are included, obviously, in any small So to say, on a metric, you can do whatever transformation you feel like, right? And in particular, it's going to include conformal transformations. So conformal transformations are included in delta G mu nu. And that means that the energy momentum tensor, this object here, it contains the information about conformal symmetry. And now I am going to sort of give you some, so this is something that you can do. I didn't declare this an exercise because it's not really a CFT exercise. It's a standard quantum field theory exercise that you can do if you've had a QFT lecture, or actually probably even just, even in classical mechanics, this is taught sometimes. You're given a field theory and you have a continuous symmetry, and therefore there results a conserved current, continuous symmetry is basically the same as saying that there is a conserved current. Let's call the conserved current J. It's conserved. And what we're going to do is we're going to take transformations as before. We're going to take infinitesimal transformations. With transformations of the type x mu. Now I'm reverting basically for this small part. I'm going to revert back to standard coordinates. This discussion really doesn't need necessarily Euclidean space or even 2 dimensions. So, but you can just run the Maynooth algorithm, and what you will find is you'll find a current which for this transformation here looks like x. Actually, let's make here of x an epsilon mu. No, that's nu of x. Okay. And now, as before, I'm just going to run through some of the transformations that we already know. So, translations, T, those are just given when I choose epsilon to be a constant. Right? When I choose epsilon to be constant, then I just pick up a translation. There's no magic there, and then I just demand the conservation of the current, and what I get from there is that the energy momentum tensor is conserved. This is something that you may most likely have already encountered. Then there are rotations, in which case epsilon mu is going to be this combination where omega, so omega mu nu plus omega nu mu is 0. That means that omega is anti-symmetric in its 2 indices mu nu. And that means from there we obtain that the energy momentum tensor is going to be symmetric in both of its indices. So this is also something that you most likely have already encountered. In a relativistic QFT, the energy momentum tensor is symmetric and conserved. That's nice. So now let's make a bit of progress. So what's new? One thing that is new in CFT is the dilation. And the dilation just is something like the scaling of the coordinate x that we had before. And when we can actually try and do that, right? So let's do that. So we demand del mu j mu, and now that's del mu t. Oops, no, I need to watch out a bit. hold on, del mu, make t nu, and then epsilon nu. Let's just do it step by step. Now we plug in del mu, t mu nu, epsilon x nu, right? So I know that the energy momentum tensor is conserved. So the partial derivative really only acts on x. But what that gives me is an epsilon t mu. Well, actually, let's just write t mu nu and then delta mu nu, and that's just epsilon t mu. And conservation demands, and this is one of the main lessons of this section. Conservation demands, or like scale invariance demands, or no, that implies, let's call it implies, tracelessness of the energy momentum tensor of t mu nu. So this is one of the hallmark thing. Like, this is a hallmark of CFT. Okay, so how can we use this? So now this, like I said, this was just basically a rehash on CFT. Here, this part here is new. Sorry, that was a rehash on QFT, and this part here is new, that the energy momentum tensor is traceless. And now let's go to 2D Euclidean space. So let's go back to the case at hand. The case at hand, 2D Euclidean case. So we have 2 dimensions. That means we have T0, 1, and we know it's symmetric, so we know that this holds. We know that T mu mu, that's something like delta mu nu, T mu nu, and that's T 0, 0 plus T 1, 1, and that's 0. So I learned that T 1, 1 is negative of T 0, 0. So what we learn here is that we really only have, so the energy momentum tensor in 2 dimensions, as it were, any tensor in 2 dimensions, or a rank 2 tensor in 2 dimensions has 4 independent components. And we learn that we truly only have 2 independent components, which is T0, 1 and T0, 0, or whichever of the other ones you fancy. And then when you go to complex coordinates, you also have, so let's remind you of the complex coordinate. Z is x0 plus I x1, and the partial derivative is 1/2 del 0 minus I del 1. And then you can look at the complex, so you look at, in complex coordinates, you look at the component TZZ, which is just defined, or you can just work out that this is related to the previous ones as follows. And T Z bar equals T0, 0 plus I T 1, 0, 1. And then conservation of the energy momentum tensor in complex coordinates. Now we really just take in complex coordinates, this equation, you can convince yourself, really what it is the following: 0 equals T ZZ. And this should be now reminiscent of the discussion that we had yesterday. So TZZ can in principle be a function of Z and Z bar, where you think of Z and Z bar as independent. And likewise, TZ bar, Z bar can also be a function of z and z bar. But conservation, you see that it forces t of zz to be a function of only z. And we're going to define, so we're going to define, actually, let's write it like this, tz. We don't always want to write the indices z and z and z bar and z bar. That's just too much. So we're going to define z bar. T of z is tzz, as many z's. And that's just a holomorphic function. And likewise, t bar of z bar is defined as t z bar, which only depends on z bar. So far so good. What have we learned now? Like just as with as the statement yesterday that holomorphic and anti-holomorphic functions are important, we find that the energy momentum tensor, which is very central to many QFTs, and to CFT it's going to be very central, is a holomorphic, has two components which are independent, and in particular written in complex coordinates. These two components are holomorphic, respectively anti-holomorphic. So this, let's just give this, let's just put an exclamation mark here. Okay. Yes.
May I ask whether it would also be insightful to consider special conformal transformations?
You want to know here? Actually, I didn't check. I can imagine what we can check. We can make that as a little exercise. What we need to check is, so if you remember, let's see, for an infinitesimal conformal, special conformal transformation, we would have to do, where is it? Sorry for scrolling so fast. Here you go. We have to derive sort of for general dimension, the analog of this transformation here, and throw that into the, so this, what it should be is just the quadratic. This should be something like x goes to x plus some number, here in this case bx squared, something like that, just as in the two-dimensional case. And then we can go ahead and see what we find. I would be surprised. So actually people never, like in the context that I just bring it up, people never discussed the special conformal transformation. So I'd be surprised if we found anything new. So my guess is that we find a combination of constraints of T being symmetric, conserved, and traceless. But to be frank, I haven't checked this, so I won't declare this as a final answer. But if you want, you can go and check it. Yeah, that's unfortunately I don't have another answer for you. Other questions? Okay, in that case, now I'm going to talk about fields and states in a CFT, and I'm going to. This is going to be when we talk about states. Evidently, we're already talking about a quantum CFT. But the first discussion that I'm going to have is about fields. And those are in principle a classical thing. I should say though, most of the time we never study classical conformal field theory. We always just talk about quantum systems. Let me just briefly outline to you what the aim is. So there is a special class of fields called primary. I'm going to explain to you what that is. And all other fields are called descendant fields. The distinction will be more concrete in a moment. I'm going to talk about the operator state correspondence. And this is a quantum thing. It turns out that every operator state correspondence. Every field, so that means that every field phi is in relation to a state phi in a Hilbert space of a quantum CFT. We're going to talk about that, and we're going to talk a bit about correlators. And when it comes to correlators, I will only talk about the bare minimum because we won't need them as much. We won't need them as much. But I should say, when working with CFT, using correlators is very important. So if you want to use CFT for your own purposes, it may pay off to go look in the literature and learn about correlators. There are powerful constraints imposed on correlators by conformal symmetry. And that's one of the marvels of CFT too. So the correlators are in general difficult to compute. Like we have these Feynman diagrams and many techniques which become rather tedious, and they're not exact, they're perturbative. And in CFT, you can solve correlators exactly by virtue of infinite symmetries floating around. Okay. So 4.1 is primary fields. Primary fields. Primary fields. So let me remind you that in the QFT, or in general, actually, always when symmetries are around, fields fall into representations of the symmetry algebra. Let me remind you, I don't know how comfortable you guys feel with the word representation. When you should always keep in your mind as a toy model or a simple example, SU2. Say a quantum system with SU2 symmetry, and then you know that there are particles with spin 1/2. They fall into a two-dimensional representation. What that means is that these spin 1/2 particles live in a two-dimensional vector space. Sometimes these vector spaces are called modules, but in the physics literature, we always call them representation. Okay, so there are spin 1/2 particles, there are spin 1 particles, those are in three-dimensional vector spaces. There are spin 3/2 particles, those are in four-dimensional vector spaces, and so on. I think you recall the drill. Okay, so, and another example, for instance, is, so in free field theory, you encounter a scalar field. So a scalar field, what it means is that if you have a symmetry algebra, the scalar field is a number for the symmetry algebra, and the symmetry algebra will only act on the argument x. For instance, if you have a Lorentz boost, the field phi is only transformed into the Lorentz boost. This now means the Lorentz boost, not the scale factor of before. And that's it. That's the only transformation. But another example, for instance, is a Dirac fermion. Dirac fermion, let's call this psi of x. So this thing is a bit more complicated. So now what you need to know, so that this thing transforms, it picks up a representation that there's going to be a matrix. What do we call this matrix? Let's call this matrix. Yeah.
You have 15 minutes left.
Thank you so much. Let's call this matrix A, and then there's psi. So the matrix A acts on psi, and then also the argument is shifted, right? So, and that means that psi is, oops, I read psi. Psi is in a non-trivial representation of the group. In this case, I just talked about the Lorentz group, right? And in CFT, so usually there are quantum numbers associated with representations. For instance, for SU2, there's the J3 quantum number. and there is the JZ, sorry, the total angular momentum squared quantum number. And in CFT, we also declare quantum numbers. So that just means like very fancy words have been used right now. And I'm going to stick with these fancy words, and you can always come and ask me what these fancy words mean. So we label representations. That means we label fields by the dilation. And rotation operator. And I remind you, so we have the, so that's the dilation and the rotation operator. And what those are secretly is L0 plus L0 bar. This is this one exercise that I proposed to you, and L0 minus L0 bar. And typically, we don't care about this I when we do this. So we just forget about the I. The I is just, it doesn't really matter much. And so these are the operators that we want to use. This is basically, instead of taking in SU2, instead of taking the total angular momentum in J3, we're going to take D and dilations D and rotations R. And we take their eigenvalues as quantum numbers. Quantum numbers. And the eigenvalues of these things are, well, if I declare, hold on, let me just write, so I need to first declare, let me start over. So if I have eigenvalues L0, L0 has an eigenvalue, yeah. I'm going to write like this, eigenvalues, it's called capital E, capital V, eigenvalues, H and H bar. So this is the standard notation that we take. And then we find that dilations and rotations are just going to be given by H plus H bar and H minus H bar. So those are the two quantum numbers that we want to use. Basically, it's up to you. Typically, we take H and H bar. So I am going to mostly stick with, no, that's not a good box. With H and H bar, but sometimes it's also useful, well, actually also for motivation, it's useful to take the dilation and the rotation operator. So this thing here is called the scaling weight, scaling dimension, and it's called delta. Actually, let me be a bit, I hope that you can still adjust on your note. I'm going to insert here. So there's delta and there's S. And now let's move here. So delta is the scaling weight and S is the spin. The spin is relatively straightforward simply because it's the eigenvalue of the rotation operator. Scaling dimensions, well, I'm just declaring that now, new for you. Okay, let's see. Okay, I'm going to talk for another like 5 minutes and then there's going to be question time. Okay, so now I'm going to introduce a bit of notation. So fields transforming under scalings scalings Z. So this is a scaling. Z goes to lambda Z as follows. So Z and Z bar. So because this is where we're always talking about scalings, I want the field to scale in a particular way. And if it scales with its quantum numbers, so there's also going to be z bar goes to lambda bar z bar as so phi, and then the argument is shifted to, just like with the Dirac fermion. So you have two things. You have a shift here outside. This is responsible for the representation, say, and you have a shift of the space-time argument, just as before. And so these fields are set. So these fields are set to have. They're said to have conformal weights h and h bar. So I didn't say this above here. So h and h bar are going to be called the conformal weight. Okay. If you remember, in SU2, representations, they're so-called highest weight representations. That means for spin 1/2, for instance, if I act on the spin -1/2 field with S minus or J minus, the negative ladder operator, then the state is annihilated. Likewise, if I act with J plus on spin +1/2, that state is also annihilated. So these representations are called highest weight. And we want something similar in CFT. I'm not going to tell you today why, but it's always useful to have them around. And actually, they're going to be physically, there's a physical reason to take these. Actually, I can just tell you. So the reason is that they will have, the energy will be bounded from below. That's the reason. But I'm going to be more concrete when the time comes. And so the highest weight fields, so now I'm going to define what these highest weight fields are. So fields which transform, or actually which mimic this behavior. By this I mean this behavior for any conformal transformation. So any conformal transformation, z goes to f of z, and z bar goes to f bar of z bar, are called, and that's the primary field. Primary fields. Primary fields of conformal weight. H and H bar. And let's put this into an equation. Oopsie. So the transformation behavior is as follows. Phi prime z bar equals, and there's going to be some transformation. Now I'm going to implicitly already assume that this is like a quantum operator thing. So I need some operation U which implements on the quantum level this transformation. And what it really looks like is del f del z h del f del z bar h bar, and then phi of f of z f bar of z bar. So this is a primary field. And just for you to convince yourself, if you pick z goes to lambda z and z bar goes to lambda bar z bar, you recover the prior, like the transformation behavior for scaling fields, right? That's why I mean what I mean by mimicking. So you see that you have a scale factor you have a scale factor which is elevated to some power h, and likewise for the anti-holomorphic sector. And the space-time argument is also shifted. So that's what's happening. And maybe a closing remark. So there are fields which transform like this. Actually, before I do that, let me just state primaries. Primaries give rise to highest weight states, but highest weight states. But I have not explained to you yet what I mean by a state. So for now, just keep this. This is just an upshot. It's nothing that you can understand with what I've told you. And fields which transform like this, and by this I mean this equation, only for global conformal transformations are called global conformal transformations. Are called quasi-primary, and I'll leave it at that. Quasi-primary. All right, so toward the end I was rushing a bit, but if you have questions, please throw them at me now.
Maybe the questions we can stop recording. So let me just give two sentences of information. So this was the second lecture for Christian. You will have him next week because on Friday you have the first lecture of Pier Alberto on mathematical foundation. Just be careful. The time is slightly different. So instead of being 2 p.m. CET, it's 1:30 CET. Okay, then I'll stop the recording.